last week we have given an introduction on single mode squeezing, right? So single mode squeezing involve, if you remember, it involved a pump and two beams with the same mode. That means they are traveling in the same direction. Okay, I've stressed that many times. If they are traveling in different direction, like this, even if the frequency is the same, this is still two-mode squeezing. Okay, very different because two-mode squeezing and single-mode squeezing have different photon statistics. Yeah, so you need to know that even the frequency is the same. If the directions are different, they are counted as two-mode squeezing.
Would they also be entangled at that time?
Huh?
Would they be entangled at that time?
Yes. In either case, they are entangled. Degenerate single mode or two mode, they are entangled. Well, actually, here you don't really call it an entangled state because it's the same state. When you call something an entangled state, you have two quantum two quantum systems, okay, and they are in certain states together. Okay, so like a two electron state.
Like a two copy of the same state in the single.
Yeah. So anyway, so this is a two mode squeezing. This is a single mode squeezing. All right, just let me make sure you understand this. Okay, so even just by changing the direction from parallel to symmetrical cones. Phoenix, would you mind sit to the front? Fine, thank you. Even just by changing direction to be parallel, the photon statistics become very different, as we will explain in the next hour. Okay, but this is important to understand. Furthermore, I want to say that the analysis we're about to give does not distinguish between degenerate two-mode squeezing or non-degenerate, which will be like this. Different frequency. This is called non-degenerate. This is also two-mode squeezing. This is degenerate. This is non-degenerate. Okay? Sorry?
They are entangled.
Yeah.
Just only for single mode is not.
Yeah, you don't call it entangled because they are in the same state. They are like, to describe single mode squeezing, you do this, NA, and that's all. Okay? There's no other state system, but here you do NA and MB. A and B represent different mode. Okay? So like if you have a two people in quantum computing will call it two qubit state, okay? But in our case, it's not qubit because it's not limited to, it's a harmonic oscillator state, so it's not limited to two-level system. Nevertheless, this two-party, okay, I'll call it two-party. Entanglement only happens when you have a two-party state, okay? When you have a two-party state, if they are in the same party, okay, in the same mode, there's nothing such as entanglement, okay? All right, so but I want to say that the photon statistics of two-mode squeezing is the same for the degenerate case and the non-degenerate case. Okay, as you're about to see. All right, so let's start with the single mode Hamiltonian. The single mode squeezing Hamiltonian, it looks like this. So this is for single mode squeezing, all right? For two mode squeezing, we can pretty much write down the Hamiltonian without derivation just by inferring this, right? Because this is single mode, you produce you generate two photons in this mode, right? And if you have not degenerate if you have two modes, then it should be pretty obvious that oh, by the way, this is 0. You will, of course, first you will have, let me just use 1 and 2, even though I write, sorry, just for consistency. Let me write 1 and 2. 1 and 2. All right. So 1. So this is the unperturbed part. Oh gosh. This is also 1 and 2. Okay. Now, here, so instead of the creation operator and annihilation operator in the same mode, 0, now it is distributed in A, in the first and the second mode. Okay? In the first and the second mode. Yes? So this is just, you can see the single mode squeezing will be a spatial case of the two mode squeezing if you have the subscript the same, right? So it's not hard to understand that this is the expected Hamiltonian.
Is there a 1/2 term in the first two terms?
Sorry?
There is a 1/2 term in the first term, because if it's like the same frequency, it will be double of that, right?
Yeah, this is just a matter of parametrization. I can define.
No, not.
No. This 2, I write this. I write the 2 here, simply because the textbook have a 2 in the squeezing operator.
I meant in the first term.
What?
In the first term.
Oh,
No.
oh, I see.
It's like if I put like.
Let me just write this in a different parameter to avoid confusion. Okay, if I write it like this.
Not in that time. I'm saying the A1 dagger, A1. No. The line. Yeah.
Here.
Yes.
Okay, what's the problem with this?
It's like if I use sense omega 0.
Oh.
Then it's 2 times that, right? So should there be h omega by 2?
That's a good question. Yeah. No. He mean that should this term be this?
Squeeze states.
He's talking about this.
Yeah,
okay. I think yes. I think the answer is yes. Okay, and that's why we are having. Oh, actually, in that case, this could be that. This is actually probably a valid point. Okay, so there are. Right. In this case. Yeah, because he's saying that if you change the subscript 1 and 2 into 0, then you have two terms. Okay, so there should be a factor of 2. He's talking about this, right?
Yes.
Okay. I think yes, that's a valid point. And remember in the last lecture we talked about how we change this into the interaction picture. so that only the interaction term, this one, is left, right? And by doing that, we get rid of the this term, right? All right. So in order to get rid of this term, you must make it into a form that looks exactly like this. Okay? Yeah? So that's where you divide the entire Hamiltonian by 2. No, sorry, you divide the entire Schrödinger equation by 2. Okay? So that's where this 2 come from. Okay? So this 2 that you mentioned actually is related to this 2, so that these are the same parameters. Okay? All right. Thanks for the question. All right, by the way, that last week in our lecture, I kind of mentioned 2 points that are weird. Which one is this imaginary number, because all our nonlinear susceptibility are real, right? We don't have any imaginary coefficients in our derivation. So like, where does this come from? Yeah, and the other one is this minus. All right. So
normally Hamiltonian has imaginary part, like if you put in the.
But in our derivation, it was not there. Okay, so the question I raised last time was like, this is kind of weird, but you kind of have to go through the entire derivation to know where it comes from. So after I go back, I did that, and I found that this is because I copied this from the textbook, and a lot of textbooks use this in Hamiltonian. I have one textbook that does not use this Hamiltonian. Okay, but anyway, I end up finding that this has to do with the textbook defining the A field as the real and the E field as this. So they put an I in the E field, in the quantized E field, and there's also an accompanied minus sign there because of the conjugate. All right, this is really just a matter of convention. In our derivation, we have the A operator just as this, right? And we have E as this, right? So this is this, and if we will just follow our convention, everything will still be consistent. If we use a different convention, then the coupling coefficient in this case will have to be imaginary. In order to give an imaginary, like this additional. So anyway, this is just because of convention. Okay, and I have wrote an email to the author of the book and asked him how, like, his opinions on this matter, because having an imaginary coupling coefficient sounds strange to me as an experimentalist. So and there is another book by Scully and Zuberi, also a very famous quantum optics book. They don't use this convention, so they use the same convention as ours, and they don't have this additional imaginary coupling coefficient. So anyway, just want to mention this so you know that there is a little inconsistency between our field quantization and the Hamiltonian will give you in the squeezing single mode squeezing lecture. And the root of that problem is just because this different conventions. This is the convention followed by in the textbook, and this is the convention we use in our derivation. Okay. All right.
So we mostly measure like the projections, right? We mostly measure the projections, right?
Make sure that
means most of, like, even if the coupling is negative, we measure the projection of that coupling.
No, no.
in experiment?
Here the okay. In our derivation, it will look like this, and the coupling coefficient is what real. Okay, even this is complicated. This is real. Okay, but in this convention, the coupling coefficient is imaginary. So it's like minus imaginary minus imaginary. It's like this. But so the two are still, these two expressions are equivalent in terms of what they do to the quantized field. It is just how we define the coupling coefficient, and that will affect your squeezing angle. Okay, it will add a 90 degree to your squeezing angle. All right, so because the squeezing parameter is defined, I think I mentioned this last time, as this. Okay, so this is the amplitude. This is the squeezing amplitude, like how much you squeeze the vacuum state, and phi is in which angle you squeeze it, the initial angle. Okay, so adding a I here will just add a 90 degree to that angle. All right, so it will not affect your photon statistics. Okay, because the angle is not in the photon distribution. Will it affect? Will you produce experimental consequences? I think yes, because like for example in the squeezed coherent state, right? Like when you squeeze the state, that initial phase does matter. Okay, but like one has to really look for it in order to see it, and it's not of a big deal. Okay, so but anyway, I bring this up to the theorist. The author of the book is a theorist, so I asked about his opinion, and he has replied me and told me that he need a couple of maybe weeks to think about it, because a lot of books use this convention, follows this convention. Okay. All right. So this is just a side issue, so I'm gonna erase it. That's not the. So that's just one thing we left, like a little loophole we left in our previous lecture. Okay. So with this Hamiltonian, again, after going into the interaction picture, we'll be left with just the interaction part. Yeah. And this again will give us, let's see, the solution. Okay, the solution of this, since it's 2 mole, so we call it a 2 mole squeezed state. Let me see here, right? We'll put a 2 here. Okay, just to distinguish with the single squeezed mode here. So we omit 1 here. So the photon state that this Hamiltonian produced can be described as sorry. Oh, sorry. 1 and 2, right? 1 and 2. Okay. And this is the vacuum field. Now the vacuum field, normally we just write a 0 to represent vacuum field of all mode. But in this case, we will focus on the vacuum field of the omega-1 and omega-2 mole. So we put a subscript here, okay? Put a subscript. Like typically I write A, 0, A and B, okay? But now I'm using 1 and 2 as my convention, so I'm gonna just stick with it, all right?
Hamiltonian INT initial mix, which modes squeezing or what?
I don't understand. What's the question?
I don't know what they symbol H head in mean.
In the action picture, Hamiltonian in the interaction picture. Right. Yeah. And so how does this work? Okay. The expansion of an exponential operator is the same as the scalar exponential, right? I talked about this last time. So it is this. Two, three. Yep. So if this is changed to an operator, the form, the formality, the form of the function still stays the same according to mathematicians. So we can do that expansion, no problem. And the end result will be we'll have photon. We have a photon distribution, a 2 mole photon distribution. 1, 2, 1, 2, and 1, 2. Yeah. So they both go from 0 to infinity. Yep. All right. So let's try to do the expansion to get a feel of the nature of this probability amplitude. All right. So according to this expansion, the first one is just an identity operator. So that does nothing. And the second one is just the set first order. Yep. Etc. So this is how it works. Now you just have to be very patient and operate each operator on the state, on the vacuum state. Okay, and if you do that, you will see a pattern. Okay, like we discussed last week. If you have a square here, right? So in the degenerate 2 mole squeezing, in the case of degenerate 2 mole squeezing, we have A0 dagger square, right? This is A0 dagger square in the single mole squeezing. So this as a basic unit in the expansion in your vacuum state, there are always going to be an increase, a basic unit of 2, right? You increase by 2. So we say that this will give you at most 2. Okay, so anything from 0 to 2 is possible. Okay, of course you need to figure out the coefficient. And here the maximum is 4, and everything from 0 to 4 is possible, but they need to do like in increments of 2. So and you need to check the coefficient, right? We played this game last week. So this is 6, 4, 2, 0. Yeah. Okay. So what happened if instead of a single mole vacuum field, we have 2 mole? We have 2 mole. Now this is not too hard. If you just look at this, you see that this is, yeah. Of course, this is just 1, 0, and 0, and this is 1, 1, right? The highest you can get is 1, 1, and the highest you can get here is 2, 2. 2, 2. Okay. Now you see our fundamental raising operator for each field is a dagger, not a dagger square. All right, so we advance by 1, not 2. So, but it always go in pairs, right? It always go in pairs, 1, 1, 2, 2. So you can imagine that from 0 to 2, 2, everything in between is possible, but they must obey 2 rules. The 2 numbers must be the same, okay? Because the operation is like act on the 2 fields simultaneously, symmetrically, okay? So the 2, whatever you have in this, it needs to be the same number, okay? NN, okay? And because this is
But we'll not have 1, 1 in that case, right?
that's just the coefficient, okay? Now we'll figure out. I'm just saying like what is logically possible, not actually evaluating the coefficient. All right. So like what matters to us now is to see what is logically possible. And you see that under these 2 rules that they must be the same and they must be advanced by 1. You can see that this is 0, 0, 1, 1, 2, 2, right?
But the 1, 1 will cancel. It will have the a dagger.
Yeah, but that is a matter of coefficient, okay? I'm saying here that this is logically possible. If you evaluate the actual coefficient, you find that this is 0, and that's okay. Okay? Actually, this is not 0. You'll see. Maybe this is 0. Okay, it doesn't matter. Okay. So here, you have 3. The highest you can get is 3, 3. Okay, and then lowest you can get is 1, 0, 0. And you have everything in between. So that's 1, 1. Everything between, they need to advance by 1. And they need to be the same. Okay, so that's the rules. 2, 2. Okay, if this rule is not clear to you, I would just suggest you to expand this and actually have the operator working on the vacuum state, and you will see. Okay.
Can you say again why there is no the force, for example, to the square A1 dagger and
So 0 acting on A like is 0. It's not like.
there's no force to it.
There is cross turn. There are of course cross turns.
Yeah, cross term is forcing 1, 1, but it will be a dagger and A.
If you do the expansion, okay, I think it's not. Okay, let me just simplify the notation. Like this. Let's simplify the notation. So I'm leaving out the coefficient. I'm leaving out the coupling coefficient, but keeping everything the same. All right.
Instead of A1 and A2, you can just use A.
It's okay. All right. So what will give you the highest photon number? That's the combination. That's the term with this, right? You see that? Oh, come on. Oh, come on. So the high, you have 9 turns, sorry, 8 turns, right? 2 by 2 by 2 to the third, 2 to the third. You have 8 turns. And out of all these turns, this turn here will give you the highest photon number, right? Okay? Now, what is the next lowest? That would be, what's the next highest? That would be this and this,
Yes, that also.
right?
There's one more term which is the same.
And of course, you have also this and this. Okay, just like a matter of combinations. So you have two that are raising and one that is lowering. Yes? Right?
You need to write opposite way.
Sorry, were they around?
Rising should be on the right. Lowering should be on the left.
Sure. Okay. Sure. Yeah? You see that? You see that? Okay. And this, so this alone will raise it to 2, okay? But then you have this that will lower it by 1. So this will give you 1. Yeah? Okay. But you can see like how this is always going up together and going down together. And it's always in the unit, like they always change by in this case, they're changing by 2, okay? But I'm just saying that you can just use this general logic of, okay, the highest is 3, okay? And I know the lowest must be 0. There's no lower you can go. And you always are changing the photon number by 1 because you have like, not an odd number, but like just 1 in each unit. So I'm saying this is logically possible. And of course, when you work out all the terms, you will see that maybe you won't have a term that is
2 will not be there.
2 2, right? You won't have a term that is 2 2. Okay? But
Also 0 will
yeah, that's just minor details. But you will find that kind of pattern in the whole expansion. When you actually do the expansion, you will find the pattern. And then that will allow you to put this in a series because there's a pattern, so you can put it in the series. Okay? All right, so if we do that, so the insight we get is that N1 and N2, if you don't have 2 in this term, right? If you don't have 2 here, you can still have 2 here, right? If you don't have 3, if you don't have 1 here, you can still have 1 here. So overall, each state 0 0 1 1 2 2 3 3 4 4 5 5, all of them will have non-zero coefficient overall. Okay? All right, so that means all these are possible. Like physically possible after you evaluate, after you expand all terms and you group them into a series, you find these are all possible. Okay? And if you look at just one of them, right, you will see that you have a distribution that goes in a continuous manner. 0, 1, 2, 3, 4. Rather than 0, 2, 4. Okay? So here the same. Here it is the same. 0, 1, 2, 3, 4. Yeah? And they will be identical. the distribution will be identical. Okay, because everything they have all the same. Yeah. Okay, so they will be identical. But now you see a very important distinction between these are the non-degenerate case. And the degenerate case, you have 0, you have 0, 2, and 4. You have only odd number, sorry, even number. And here you have all the numbers. Yeah. Okay. So now a little bit of physics. So now you see that here you have, it is pretty clear you have pair creation. Pair, one in this mode, one in this mode. Always pair, right? And in that in the degenerate case, that two pair, that the pair, each one photon in each mode, that kind of just merged into the same mode. So instead of pair, you have even number states. So this is a pair state. This is not a pair state. Okay. Yeah, of course you can say that two photons are excited together. Two photons are excited. They're kind of a pair. Okay, but I think it's clear that this is a pair because they are in different modes. And here, yeah, you can say it. You can like try to force the terminology, but this is not really a pair. This is just two even excitation. All right. So you see that by simply considering having the detector here and the detector here, they give you if your detector can read photon statistics, they will have very different photon statistics, right? In each bin here, you have this one, this continuous one, all right? So I need to speed up. So this, by the way, this we call the two-mode squeezing operator. So, and just let me write here, the squeezing operator is defined as this, as last time, okay? It has amplitude and has phase. I mean, it's just a general complex number, and we parameterize it with amplitude R and phase phi. So this two-mode squeeze state one and two is, now since they are pair, we don't need to use N1 and N2. 1N is sufficient because they are the same number, right? So you just go from 0 to infinite, and this is the coefficient. R, N, cosh R, and N. Yep. Okay.
That 10 is not on the E power, right? It's different.
We have not included 10.
No, 10 it means like no, it's okay.
If you want to include, yes. If you would include 10, then that will have additional vector, like I think it will have an additional vector like this, t, I think. Okay? Yeah. All right. So what is this? This looks very complicated. This looks really complicated, but it is not. Okay, so let me just write I goes from 1 to 2. So each state. Let me just write it this way. Each state, each mode have the same. You can see that each mode have the same photon distribution, and that is this.
So how was on your
R. R represent the coupling strength, which also include the pump strength. So R is a function of, say, your nonlinear susceptibility. Yeah, it's the amplitude. R is the amplitude of the coupling coefficient, right? So we should stress again that this coupling coefficient is now replaced by the two parameters R and theta. Yeah. Okay, and now the following statistic is the same, as I said. They look like this, hyperbolic functions. And if you try to calculate the average photon number in each arm, okay? So say like here, this is the average photon number, and here is the average photon number. They must be the same, right? Because the photon statistic is the same. So the average photon number in this case will be sinh, okay? Sinh R. All right, maybe I should put a little bracket here. Yeah. With these two together, you can simplify this expression greatly. You can simplify this expression greatly. Let me show you how to do that. So tangent here give you, that's sinh divided by coach. So sinh divided by coach, and coach, that'll be coach 2n, right? And combined with this, that'll be coach 2n plus 1. Yep. Yep. Now, wait. Yeah, a second. Oh, sorry, this is square. Okay. And I missed a 2 here. I'm terribly sorry. I missed a 2 here, so that is 2. Okay. All right. So we can put this 2 in. So that's coach 2, right? And coach 2 is related to sinh square. Coach square is related to sinh square by by this relation. Yeah. And here you still have, here you have this, right? So you see I deliberately put the 2 to the power of sinh because I want to replace them by the photon number. Yeah. So you see that now here the photon number is, so they are just this equal to the photon, the same photon number, n, and this is n plus 1. Yeah. Okay. And this distribution is exactly the same as the thermal distribution. Okay, thermal light photon distribution. This is equivalent. So the thermal light, the thermal light photon distribution. So you start with the Boltzmann rule. You start with the Boltzmann distribution, right? And here you have this thing called this Z. That's basically the partition function, which is the sum of all these terms. Okay, and then with a lot of math, you can simplify this to n plus 1. Yeah, and here your n is solved through this equation. Yeah. Okay. So this is a thermal light photon distribution. So say you have like, yeah, like a Planck spectrum. I wonder if it's a Boltzmann spectrum or Planck spectrum. But anyway, this is the thermal light distribution. And here you see that n, the average photon number, is associated with the temperature. And that's understandable, right? The higher the temperature, I mean, the hotter the light, the hotter the body, more photon flux it emits, right? So using the same terminology, you can define an effective photon, an effective temperature for this light field. Yeah, and you can imagine that temperature, that effective temperature, is basically the same. It's just another way of expressing the coupling strength, the coupling coefficient. Okay, and so I'm just gonna give you the expression here. 2kb 1 over natural logarithmic cotangent is rather complicated. Okay, so it goes like this. Okay, at the first sight, it's kind of strange to have r in the denominator, right? Because you would think, okay, r should be proportional to the temperature, so it should be, in the numerator, right? But if you notice that the cotangent function, the hyperbolic cotangent function, goes like this. Okay, so if this is r and this is a cotangent h, it approaches 1 for very large squeezing. Okay, very strong squeezing, very strong pump. This will approach 1. Yeah, and the logarithmic function is 0 at 1, right? So that means this term will approach 0. This will approach 0 for very large squeezing. Okay, if this term is 0, this term will, the inverse of it will go pretty quickly, like rapidly up. Yeah, so this is indeed, the temperature is indeed going up with R. So this definition of effective temperature makes sense. Okay. Not that you should compare this with the real temperature, but just to give you an idea of how hot your thermal light source needs to be in order to match certain pumping strength. Okay, since they have the same photon statistics. Okay, so that is just one thing. All right. Next.
This temperature has nothing to do with like.
No, this is not real temperature. Yeah. This is just like for parameter comparison.
Means normally
if you want
like a cryogenic temperature or something,
no,
you can get a better squeezing rate.
No, this has nothing to do with that. The cryogenic, why would one want to do cryogenic temperature with in the squeezing experiment?
No, means like if you want to make your better squeezing, reducing other noises with cryogenic temperature.
No. Well, one thing you can do is you can estimate for room temperature, okay, thermal distribution for room temperature. What kind of squeezing parameter does that compare to? And you can compare that squeezing. You can compare that room temperature, the comparable or the R effective. See how that compares to your actual pump strength and your coupling coefficient of your crystal, and see if that is negligible. If it's not, so say you have a very, very weakly coupled nonlinear crystal with very low nonlinear sensibility. I don't know why anybody would want to use this, but say if you have such things, right? And and because the coupling coefficient is so low, even if you use a very strong pump, R is still pretty low for that one, and that is comparable to the effective R from the room temperature. In that case, yes, of course, you may want to like cool the entire detector, like around the detector, so that it does not receive thermal light from the background. You might want to do that, okay? But if it's much, much weaker, like 2 orders of magnitude weaker, then you don't even need to worry about it, yeah? So this is just something maybe of practical use, maybe not, I don't know. All right. Now we want to talk about something else. So in the lab, it is very important to realize that we are using 2-mole squeezing instead of a single-mole squeezing. Single-mole squeezing is simpler theoretically and mathematically, and 2-mole squeezing is slightly more complicated. And in this lab, we're using 2-mole squeezing. Okay. Okay. Now I want to talk about something else. The landmark Hong-Ou-Mandel aspect, or Hong-Ou, they are all French, so maybe R is pronounced as so Hong-Ou-Mandel aspect experiment, called GRA experiment. Yeah. In this experiment, they demonstrate for the first time in history of quantum optics this is 0, and this is delay, this is G2, right? Remember I told you that whatever is above 0, so G2 equal or larger than 0, this is the classical region. Okay, classical theory can predict that light given this behavior. Okay, you might have different mechanism for your light, but they are all gonna give this behavior. Therefore, if you have, I'm sorry, this is 1, not 0, this is 1. Okay, and 0 is here. 0 is here. Okay, so I'm just gonna mark it down there. If you have, let me change this too. If you have a correlation that is smaller than 1, okay, this will be deemed as non-classical, right? Because it's not in the domain of classical electrodynamics. So it's non-classical, and non-classical means quantum. Okay? So there are the first one to demonstrate the quantum statistics of photon fields. Okay, and they do this not with the experiment that we did, not with the same experimental setup we did. They do this with a probably, I think, conceptually simpler system. They use a sodium calcium atom, and in this atom there are 3 levels. There are 3 levels. Okay, you have the ground, you have the excited, you have the median. Okay, or maybe I should say this is median, intermediate, and this is excited. Okay, so they first figured out a way to get this atom, this population, go from ground to the intermediate state. So they bypass the excited state that is in the middle. And then they just wait. Okay? They just wait. When this decay is a 2-step decay, it's like a cascade. It's a cascade type of decay. So you first go here, and then you go here. All right? This happens in sequence. There, of course, is a little time delay in between, but this happens in sequence. The light that is emitted from the first step is a green light, 551 nanometer. And the light emitted from the second step is a blue light, 423 nanometer. Okay? So and of course this is fluorescent, so it goes in all directions. So here you have also 551 nanometer, okay? And here you also have 423 nanometer, okay? Now, what they do is they put a filter on this side. Filter. And a photodetector, right? So this filter will take the 551 nanometer light, but will block out the 4323 nanometer light. 551. Okay? So they use this filter as a trigger for the detector on the other side. On this side, they also, of course, they use another filter. Filter 2, and this is the filter 1. Oh, maybe I should just write filter A and filter B. Okay, and this is detector T for triggering. Okay, and after filter B, you have 423 nanometer. They are spectrally far enough. You can use filter to separate them. Sometimes you have like light that are very close. The difference is like 1 or 2 nanometer. Then it will be very difficult to separate them. But in this case, the difference is 130 nanometers, so it's pretty easy to find a proper filter to separate them. So basically, on the left-hand side, you have detector for 551, and on the right-hand side, you have detectors for 423. And what they do is they put a beam splitter here, yeah, and also detectors on both sides. So this is This is Hambre-Brown twist. This is the Hambre-Brown twist setup. So this is a Hambre-Brown twist measurement. Yeah. By itself is a Hambre-Brown twist measurement, and it measures the correlation, the autocorrelation in the light field. Now, since this is since whenever it emit a 423 photon, it is always a single photon because the energy from the atomic system is enough for a single photon. So you won't have two photons. There's no way. There's just no energy available. So every time you produce light here in this wavelength is always you produce one photon at a time. Okay? So photon statistic is pretty obvious. It is one photon. And the rest of the states are zero. The probability is zero. Okay, this is one photon. So when the photon gets to here, of course you cannot split a single photon. Yeah? So you will either go this way or this way. And here you will have an anti-correlation, a dip. But without the trickling, it is difficult to see that single photon from this background. Even if you dim your light and close all your windows, there are still background light. Even thermal radiations from your body can affect the detection. Okay? So you need to pick out that single photon signal from this background. How do you do that? You use this as trigger. Okay? This triggering signal from 551. This precedes before the emission of 4 to 3 nanometer photons. So this herald the presence of the incoming of the 4 to 3 nanometer photon. So it's called heralding. Okay? Or you can call it just gating. Gating means you turn on the detector. Okay, so there's like a power switch here. So there's a little power switch. Okay, you either turn it on or off, depending on your incoming signal from here, 1 or 0. So you gate it. So it's a gated. So in a gated Hambre-Brown twist measurement, they are able to see the distribution. But I want to say that even if, like, assume in the perfect world, you don't have this background, okay? You do the experiment in such a, I don't know, like a space. You completely shield out all thermal radiations. In that case, you don't need this gate, okay? This gate is to help reduce background. Okay? In our experiment, the gate is not for this purpose. It's for another purpose. So that's where the confusion can come, right? I just want to say here, even before the detection, this is a single photon distribution, okay? It has always been a single photon distribution. It does not depending on whether you gate it or not. It always is a single photon distribution. It's just for technical reason, we want to gate it so we can reduce the background noise, okay? But in our experiment, it is more complicated, actually a lot more complicated. And it actually took me a while to figure this out. First, I have to, like, the first thing I found is that this is not single mode squeezing as people usually talk about when they talk about squeeze state, or when they talk about like parametric generation, down conversion, parametric generation. Like, that's the first thing I found. This is 2 mode squeezing, not single mode. And the second thing I found, which I will explain here. Okay, in our experiment, we have this pump for 5 nanometer, I think, and this pump on a BBO crystal, right? And out of the BBO, there are 800 nanometer line, and we block out the pump. Okay, we block out the pump. And in one arm, we have a detector, okay? And in another arm, we put a beam splitter and 2 detectors. Okay, this is our experimental setup. This is called, in our experiment, in our menu, this is called a GRA experiment by FOLAB, because this mimic the detection scheme they have here. They have a trigger, so you know they have a Hambre-Brown setup measurement. So our measurement is important. Our measurement setup is also gated, Hambre-Brown, gated HBT, sorry, gated HBT measurement. Okay? That's the similarity between our experiment and the original Hong-Ou-Mandel aspect experiment, GRA experiment. But that's as far as the comparison goes. Only in the measurement setup. But the photon statistics in the light is completely different. Completely different. Okay? In this case, we have a genuine single photon, right? But in our case, like I just explained, in each light, in each mode, you have a continuous distribution. Yeah? You have a continuous distribution. You have like a thermal distribution. So how in the world can we use such a source? I mean, how in the world can we see anticorrelation from such a source? Right? And this is how. There are 2 reasons that we are seeing. So by the way, the Hambre-Brown measurement that we get is also below 1. Okay? It's also below 1. Okay? So like how does this happen? Because here we have a thermal distribution, for crying out loud, right? Well, this could happen because number one, we choose to operate in the weak pump limit. Okay, that's very important. Our pump is very weak. It's actually quite weak, probably just a few milliwatt, I think. It's not strong. So our squeezing factor is low. Okay? Weak pump limit. And this will produce for us a distribution with maybe, I don't know, like 70% in the vacuum. So not much change from the case with no pump. And we will have some in the first. Okay? And we have negligible amount in 2. Okay? So this is what we have. Now, what happens if we do strong pump? What happens if we do strong pump? Like to actually get this, Well, then in that case, so this is 0, this is 1, this is 2, this is 3. So this means at each instance of photon generation, you could have 3 photons together, 2 photons together, 1 photon, 5 photon, 1 photon, 2 photon, okay? And these are the frequency that happens. And the photon number here represent the field strength. Okay, so remember, it's not like individual particles that you should like catch them. No, it's not like that. It represents the amount of your field amplitude. Okay, your field amplitude and your mode function has a particular your field amplitude has a particular value, like a fixed value for when you detect a 2 photon state. Okay, and also your mode pattern has a different distribution. Okay, and that has to do with the Wigner function we talked about last week. And so each one of them is 2. Okay, so I'm gonna use. So if this is like a timeline, I'm gonna just use 1 dot to represent 1 photon state, 2 dots represent 2 photon state, and 3 dots represent 3 photon state. Okay, and they are generated in sequence, but they are together. Okay, so in this series of photon generation event, you could have, sometimes 1, sometimes 3, sometimes maybe 4 once in a while, or 5. And this is 1, 2, 3, like this. Okay, so each instance you have 3 photon, 1 photon, 1 photon, 2 photon, 3 photon, 1 photon, 2 photon, 1 photon, 3 photon, 5 photon. Okay, it's like that. Now, if we have an appreciable amount of probability in, say, even just 2 or 3, okay, I think 3 will be very easy to illustrate my point. So if we have 3, then in principle, there's no way to cancel. There's really no way to cancel out, even by quantum interference. There's no way to cancel out your bin in one of the port. Okay, so you must. So if you have a 3 photon state, you must have in. Okay, in each bin, in each arm, some photon. Maybe this is a 2 photon state and a 1 photon state, or this could be a 3 photon state and a 0. Okay, but all are possible. This, of course, will give you an anti-correlation. Yeah, but so this will give you this, but this will give you a positive correlation. Okay, so together, if you have a strong pump, together they'll give you something like this. If you increase your strength, this knot will be lifted up. Okay, if you increase it strong enough, you will go to 1 and even go to 2. Okay, so these are the strong pump limit. So this is, yeah, and if this is if this exceeds 0.5, it's no longer a good heraldic single photon source. So that means if we want to use SPDC, if we want to use SPDC generation to make heraldic single photon source, that means we are limited by the flux. Because if we pump too strong, the photon statistic will be too bad. Will become like bad enough that we cannot use it as a single photon source. But if we operate with, modest pump, then our photon flux is pretty low. Okay, so you see that this is the intrinsic physical limitation on SPDC heralded single photon source. Right? I think it's very important to realize that. For atomic single photon source, you can pump it as hard as you want. You will remain single photon. It will not change. But when you pump this really, really hard, the photon statistic will change. Okay, and this has been experimentally shown, demonstrated. Okay. So there is one experiment. So this is just like one.
If you have a high pump, we can only produce classical.
Yeah, you will see really the single photon. Sorry, you will see the thermal distribution, the thermal nature of this. Okay.
You can only detect the thermal. It's not like you can. It is.
It is thermal, and the photon distribution will be like this. Okay, and this is far from single photon. It doesn't matter if you detect it or not. It's even detection is like the least criteria. What it really is versus your detection, right? Okay. Let me not, because we're again running out of time. So this is what happened in our experiment. Okay. So we are pumping it really low, small, like this. Now you might wonder, okay, if I have this photon statistics and I just use HBT. Oh, by the way, in the strong pump limit, it doesn't matter if you gate the detection or not. You will have a positive correlation. It doesn't matter if you gate it. Yeah. So gating has nothing to do with collapsing the wave function, whatever. Have nothing to do with that. Okay. There are places where you use the entangled property of the two beam, but not in our experiment. The second thing is, okay, you might wonder, okay, maybe if I need to operate in the weak pump limit, this is pretty much, okay, of course I cannot detect this. I cannot detect the vacuum field. I can only detect this. So this is pretty close to a single photon distribution, right? This is like this is the same as a common notion that a lot of people will have. If you crank the pump, if you crank the laser, lower the laser intensity enough using a filter, using like 1,000 filters, like ND7 or 8 or 9, to bring the energy flux down to the equivalent of a single photon, then you'll have a single photon source. In that case, they are talking about Poisson distribution like this, okay? A lot of people think this is like, this will give you a single photon source, but it will not, okay? In the G2, so this is a weak coherent light. So weak laser. In this case, the G2 will still remain 1 because this is intrinsically Poisson distribution. So it doesn't matter how low it is, will always be 1. But in our case, we have a different distribution. It's not Poisson distribution, it's thermal distribution, right? So maybe a thermal light, a very, very low temperature, like almost close to cryogenic temperature thermal light, that could be used as a single photon source. Okay, some might think. Okay, so this is a weak pump SPDC light. All right. Well, unfortunately, in this case, and actually one of the lab asked us to do this. You cut the gate. You cut the gating off. Okay, you don't gate it. It doesn't matter if you detect the photon or not. You don't gate it. And then here you will measure the HBT correlation coefficient, and then you will find that this is still the same, close to 1. Okay. So what is going on here? This is very puzzling to me. All right. In the weak-point limit, why do we still get this? Because the photon statistic is not Poisson. It is this, and this looks like not far from single photon distribution to me. Okay. All right. So what is happening is that in our detection, we have coincidence versus, so two detector click together, right? Versus individual clicking times individual, right? So if we basically take 3 measurements. We have 3 datas. One is just clicking from one detector, click. We record everything here, and then we record also click from the other the other detector, right? So these are our baseline. These are our denominator, baseline, and guess what that will be? That will just be your individual click, would be. So in this case, we have most of the case single photon, right? And so single photon should go either here, and this is 0, or here, right? So we will see single photon click in our individual detector. Okay, so this probability will follow P1. Yeah. And if you remember the formula we have, Pn equal to 1 over n, right? Then P1 will be n2. Yes? Okay. Now, when do you get coincident count? You don't get coincident count with this state. Yeah? You get coincident count with this very, very occasional, like super rare 2-photon state. When you have 2-photon state, yes, you have 1 here and 1 here. And that's where you get coincident count. Yes? So this is P2. This probability is equal to P2. Okay? How much 2-photon states are there in your photon stream? Yeah? But this is equal to how much single photon states, or actually all of them, but the majority is P1. The majority is single photon state. So this is overwhelmed by P1.
P2 will also have some single photon state, like 2, 0.
Right. Yeah. But this must, right? Sure. But the maximum of the coincidence is limited by P2. Okay. So let me just approximate this with that. So this is this. Okay. Now this is the magic. So this is the second thing I found. And let's just make everything. They make everything so difficult. So this is what happened. And if you do the math, you will see this is 1 plus. If you just like take this 2, okay, you square this, and so you take this and divide it by the square of this, and you get 1 plus this. Yeah. So you see, it is always larger than 1. And that's why you get, even in the weak count limit, even with something that is so close to a single photon distribution, okay, you still speak, because this relative, the ratio between 2 photon state and 1 photon state is fixed by this number, okay? So this is, yeah, this will give you a constant, a G2 equal or larger than 1. Actually, always larger than 1 because n is not 0. So this is larger than 1. Okay? So that's why the interpretation of our experiment is so much harder than the original Hong-Roger aspect experiment. Okay? All right, I think maybe we should call it off. Yeah, because we did very long lecture last week. And yeah, so you'll be, yeah, because if I want to cover the classical spin, that's probably at least 1 hour, another hour, and that will put us to 5 again. Okay, so let's just cut it off here, and next week we'll do a spin lecture. Yeah. All right. So okay, that's good. All right. So we'll do a quick break, 5-minute break, and then we'll come back for peer instruction quiz. Okay. Okay, are we 5 minutes yet?
Oh, you're ready?
Yeah, I'm waiting. Is it 5 minutes already? All right. We're gonna wait for 30 seconds.
The first one is feature rate and second is non-feature rate.
Yeah, I mark it. All right, great. So the 2 questions are on the board. You can read it. The first question is the photon statistics descent in the 2 arms of degenerate 2-mole squeezing. Yes or no? Please stand up and get in a line or 2 lines. Get behind your answer. Right? Move, people. Why are you not moving? Why are you not moving? Move. It's very strange. Are you all bosons? Like one person move, the other move as well. One person sit, the other person sleep as well. So everybody choose yes? Okay. All right. You two will debate, and you will debate with me. I'll be your debate partner.
Like in the degenerate case, we will have always two.
So you're wrong, obviously. You're wrong, and you should consider switching to the other side.
We have one in both states. For single
See?
for the statistics,
You feel like
yeah,
this is not a good answer, right? You want to go to the other side.
Statistic means like it's not like each what we are using like
It's a result.
but we are not looking at like only a single event. So in both, like if there is like it goes 1 here and 0 here, but next time it will be 1 and 0 here.
Are you sure?
Yes.
This is a single photon you're talking about.
Yes.
And why does this has anything to do with single photon state?
If I get like single photon here, sometimes the photon just go here.
But you can also get two photon, right? You can also get more multi-photon side. I don't know why you limit yourself to single photon.
At that time, multi-photon, like if it's going 1-1, it's the same statistics in the both time, right?
You sure?
Yes.
I'm not so sure. Are you sure this is the 2 arms?
Oh, no. The arms are the other one. Oh, sorry.
You see? You should just
no,
switch
no,
to the
no,
other
no,
answer.
no.
All right, hands up. Hands up. Hands up. Okay, you guys should all consider switch to the other answer, right? Anybody? Anybody want to switch? Okay. If not, are you convinced? Are you convinced? Are you convinced? Okay. Everybody's convinced, then I guess there's no point to do another round. Okay. The answer is yes. So, okay. All right. Now the second question. The photon statistic is the photon statistic the same in 2 arms of non-degenerate two-mode squeezing. Okay. In this case, do you want to choose yes or no? Still want to choose yes? Okay. Who want to debate with me?
You told at the beginning of the class, non-degenerate and degenerate, the statistic is the same.
Okay. Okay. You two will go in one group, and you will debate with me. Okay. Phoenix, you're wrong. You should consider choose the other answer.
We can get
but
degenerate or non-degenerate.
in class,
We will have the same photon statistics. We
the
cannot distinguish.
result we get is, for example, there's
If the first one is right, second one
and
is also right.
like each of one arm of the mode will have like is photon distribution is even though their I mean, they will share the same statistic, but not. I mean, how can I say?
See, it's not very convincing.
I mean they for this one is for N1 and this one is for N2. Right. But it's because normally they go in the pair, so you also have this one is the photon distribution for I mean,
is it this degenerate case or non-degenerate case?
Non-degenerate case.
Okay.
Degenerate case it will be go in like zero, with 0, 2 or 4 something. Like it's like even number, but this one is
So
this one is so it says 2 and 0. This one and 1 and 2, but I mean
so for the first question,
this one
there are no two distribution. There are only one. There's only one distribution.
yes. It's like share the same.
They are the same. Both are like this. I see. I think that's wrong. You think?
No.
I really think that's wrong.
Why?
Because when you have this degenerate case, right?
Two more squeezing.
Yeah, these are two more squeezing.
Yeah, but
This is degenerate two more squeezing, right? And you can have 1, 1 here, so you should not have 0. Or you can have 3, 3 here. You should not have 0.
oh, okay. I think we are talking about okay. This one is for single mode. Okay, this one is 2 more squeezing, but it doesn't matter. It's
Okay,
same.
so see, the degenerate 2 more squeezing and single mode squeezing are different.
No, it's same.
Okay, all right, I'll leave you there. All right, anybody want to change your answer? So you want to do yes? Want to do yes? Want to do yes?
Yes.
Are you fully convinced?
Yes.
All right. Okay. All right. You guys. That's right. Correct. All right. Cool. Congratulations on all earn this point. Okay. Now let's go to the lab and work.